Hello everyone! Thank you so much for joining us today as we discuss polymers and plastics applying Raman spectroscopy to improve today and change tomorrow. I'm Carrie Burton, your Renishaw host for today's webinar, and with me is Tim Smith and Sarah Scheidler. Before we begin, please note that you are on mute and will remain in listen-only mode throughout the webinar. We encourage you to submit your questions or comments at any time during the session using the control panel on the right side. We will be answering as many questions as possible at the end of the presentation, and we are recording today's webinar and will be sending the replay to you via email. And now I'd like to hand it over to Tim Smith, Raman Application Manager at Renishaw PLC and Spectroscopy Products Division. Good afternoon, Tim.
Thank you, and welcome everyone to this Renishaw webinar, where we're going to be talking about polymers and plastics and how we can apply Raman spectroscopy to really understand and improve these materials. So I'm going to be talking about the role that Raman spectroscopy plays when in the analysis of polymers, the kind of information that we can produce, and what we need to consider during that work. I'll talk about confocal Raman analysis, particularly of laminates where we have multiple polymer layers. And I've got several case studies to talk through where we've got multiple complex layers, some of those being very thick, and I'll explain how we go about analysing those types of materials. And also where we have very thin coatings, often at the surface of things like adhesives and silicones, and how we can optimize our configuration to get information from these things as well. And then I'll look at Raman imaging of sections. So instead of looking at depth into the material, we'll take a section and then we'll perform conventional Raman imaging to understand what's present. And there are some benefits in performing work in this type of way as well. So I'll explain what those are. So then I'm going to pass over to my colleague, Sarah Scheidler. She'll be talking about microplastics and how we can optimize our setup to identify microplastics, but also the role we have in being able to improve the products that we currently produce and make them more environmentally friendly. And we've got an example here investigating a biodegradable plastic candidate where the sample's been aged and we've been able to use the chemical information to understand what's happened during the aging process. And then at the end, we'll kind of conclude our findings. Polymers are fantastic materials. They've got fantastic properties. And what really we want to focus on in this webinar is how we can use the different analytical techniques we've got, including Raman spectroscopy, to be able to produce better products, cheaper products, and products that are more environmentally friendly, so that we can keep using these, but in a more sustainable way as we go into the future. And to some extent, they've been so successful. It's primarily why we're in the position we're in having to try to monitor some of the issues that the plastics themselves can cause for the environment. So what information can we get from Raman spectroscopy that's relevant to polymers? Well, it all really starts with the ability to identify different materials chemically. So for Raman spectroscopy, we've got really high chemical specificity. That means it's very straightforward to look at different polymers, look at other organic materials such as adhesives or silicones, and be able to understand what and identify that material. It can also be applied to inorganics and dyes. So really, most materials produce a Raman spectrum apart from some metals. So it's a very versatile technique. And in the context of laminates, that allows us to get spatial information as well. So things like the thickness of any layers, of course, the order of the different layers, and any kind of variations and interactions that happen between the layers that are so often important to us in that type of work. In terms of the spectra themselves, so here I've got an example where I've got different types of polypropylene. We've got isotactic, syndiotactic, and chlorinated. So you can see lots of similarities between them, but also quite a few differences. And we only need very subtle differences to be able to get the specificity we need to be able to identify the material. And this is what makes Raman such a powerful technique. So as well as pure identification, we can also look at some of the properties of the materials using Raman as well. So that can be things like crystallinity and stress and strain as well. So here in this example, I've got some spectra from polyethylene, and we've got the Raman band at around 1300 wave numbers. This is insensitive to crystallinity, so we can use this as somewhat of an internal standard, whereas the Raman band at about 1416 wave numbers, this is very sensitive to crystallinity changes. So we can then calculate in a really simple way how crystalline the material is. So here you can see that the polyethylene sample in black has much lower crystallinity compared to the one in red. We can also, as an example, show you the changing crystallinity we can monitor over time by heating and then cooling a polyethylene sample. So here we've got a plot where each data point represents the collection of a Raman spectrum. On the x-axis here we have temperature, so we're going to go through the process of heating and then cooling the sample. And on our y-axis we've got the z position, the height of the sample. So to start with, we have the sample at room temperature, and we've set a nominal height at 0. As we heat the sample, it starts to expand, so the surface becomes higher, and it gets to a point here around 150 degrees where it starts to melt. So at this point, the crystallinity starts to reduce. That means we get a broadening of some of the Raman features. As that becomes a liquid and melts, it becomes completely amorphous. So this is the completely amorphous spectrum of polyethylene. And of course, the height starts to change because we go from being a pellet to melting and taking the form of the crucible. So the liquid then spreads out and the height drops. As it then fills the crucible, it then starts to cool, and we can monitor the cooling. It then contracts and the height becomes lower. And then at the end, we get back to a crystalline version of the solid polyethylene. So this is an example of a heating and cooling experiment showing both the ability to track the height change of the sample using some technology we call LiveTrack, but also being able to get the chemical information to understand what's happening with the material, and here in particular interested in the change it's had on the crystallinity. The Raman spectroscopy technique itself is really well suited. Apart from the information we can get, because it's an optical method, it means that we don't have to contact the sample and it's non-destructive. So we use a laser. That laser can focus through transparent materials and there's no damage caused by that laser. That means we can reuse and reanalyze that same material using different techniques. We've looked at the chemical specificity and shown how high that can be, but we also benefit from having really high spatial resolution. That's both lateral resolution in X and Y, and then axial resolution, which we call confocality, and that's along the plane of the laser focus. And having that confocality combined with the specificity is an ideal combination to be able to look at laminates without having to section them at all. So when analysing laminates, we really want to optimize for our confocal setup. So to do this, we generally want to use a shorter laser wavelength. So in this work, we've used a 532 nanometer laser. The shorter the laser wavelength, the higher the confocality. We want to use high magnification and NA objectives. So NA is numerical aperture. Again, this gives us a really high confocal performance. And confocality, I talk about high confocality That's basically having a small collection volume where we're getting Raman information which is very, very specific to only a certain point, throwing away light outside of that volume and giving us that high spatial resolution. And on the InVia Qontor Raman microscope we have a really simple method to optimize the system itself to give us the best confocal data, and that's called easy confocal mode. But it all starts really for a laminate with how we can prepare the sample. And it's really straightforward because preparation is very simple. So here we would generally use a plate that's inserted onto the sample stage. The laminate is held below this magnet. The magnet's got a hole, so obviously we can access that sample with the collection objective, focus a laser onto it, and collect our data. But the magnet allows us to hold the sample without it moving around in the X, Y, or Z position and make sure it's really stable for us to perform our measurements. So how do we go about analysing the different laminates? Well, the confocality we've talked about is really important, and probably the most important part of this is deciding which objective to use to collect our Raman data. And this really falls into two categories. One is using an air objective, and the other is using an oil immersion or an immersion objective. So for an air objective, we have our collection optic, we have our light being focused down to a single point, and then we have our material in blue. So for this type of work, what we generally do is perform a depth profile. That is, we move the sample up through the fixed laser point multiple times, collecting a Raman spectrum at each point, and this allows us to be able to get this chemical information to understand what's present at that position and how thick is that layer. Of course, if we're using an air objective, we have between the objective and the sample just the air itself. And of course, that means we have the refractive index to consider, where the light is refracted at the interface with the sample, and that means it's refracted down into the sample deeper than it would otherwise be. So as we move our sample up, you can see that even though we've only moved the sample a distance of x, we're now actually analysing, because of the refraction, a depth of nx, where n's the refractive index. So you can see as you go deeper into the material, then it becomes harder to understand how thick that layer would be, because it's harder to understand where we're actually analysing inside the material. Because of this, oil immersion is a really useful option. With oil immersion, you basically have oil sandwiched between your objective and your sample, and you can use a cover slip. So you can have a cover slip on top of your sample, and the oil can then be in touch with your cover slip as well. But either way, the whole premise is that you don't have any air. Your oil is effectively refractive index matched to your sample. And that means that we don't have to worry about the refraction, and we end up collecting data from effectively where the dotted lines are on here. And you can see that's the same distance as this distance the sample was moved, x. So it makes it much simpler to understand how thick layers are. We get much better collection efficiency, particularly as we go deep into the sample, because there are more losses at interfaces. And you can also see that as we go deeper, we're going to maintain the same focus point in depth, even from light coming from different parts of the optical element are still focused to the same point. Whereas if you're using an air objective, you can see that these are actually focused to different points. That means as you analyze deeper into your sample, you're becoming less confocal, and it's going to start to blur out some of those layers that you might want to see. So oil immersion might sound quite complex. It's really straightforward to perform, just using the right objective, pulling a drop of oil between your sample and the objective, and then you physically immerse your objective into that oil. So all the work we're doing here is using the InVia Qontor confocal Raman microscope. Some of the key features of this system that are relevant to this work that we're going to perform are the easy confocal option to allow us to get the optimized confocal performance. It's optimized for high magnification and high NA objectives. And you can just use an oil immersion objective straight with the system. There's no other setup you need. And that gives us the ideal configuration as I've shown for laminate type work. We've got really high throughput, which means we can get our data nice and fast. That really helps with things like stability, where environmental factors might be a consideration. And if you can get that data quickly, then that's going to help as well. We've got native really high spectral resolution. This allows us to have really sharp Raman bands, and this means that similar materials can be differentiated. That gives us our high specificity between similar materials. If we want to change from one laser wavelength to another, then we can do that really easily just by a single click in the software. Most of the work performed here is using a 532 nanometer laser. This gives us our highest spatial resolution. But sometimes where we have dyes, or where we have materials that maybe give us some kind of fluorescence, then we can change to a 633 red laser, or maybe a 785 sort of near infrared laser as well. And this system has live track focus tracking integrated into the system. That's not really relevant for the depth profiling work, but certainly as we get on to looking at sections, it can give us some really complementary information, both giving us high spatial resolution for the chemical information, but also allowing us to get topographical information from the surface of our material. So the first example I want to talk through is looking at a complex laminate. So this will be using oil immersion, and we're going to be doing a depth profile. So we're going to have our focus at a single point in space, and we're going to be moving our sample up through that focus, collecting a spectrum at each point, and then being able to identify what the spectrum is at any given point to produce a profile. So here we've got quite a complex laminate. I've used a 0.5 micron step size, and this is given us a 290 spectra. So this x-axis here, so 0 is the surface of the material, and as we go to the right, we're basically moving that material up through that point, and that represents the distance that we've traveled. So above the surface, we've got our oil. I've got this schematic at the top here to kind of help clarify these profiles. But effectively, where we've got a color that's high, it's showing you that that material is present, and where it's low, it's showing that that's not present, it's absent. So you can see here, we've got 7 different layers and 5 different materials observed. Because we've used oil immersion, it's also really straightforward to quantify the thickness of any of those layers. So for example here, the polyurethane layers are about 4 microns in thickness. And also because of the oil immersion, we've got really high efficiency, even deep into the sample, so well over 100 microns in depth. If we were using an air objective, we'd be very limited down to around 10 to 20 microns at most before we start to really lose a lot of Raman signal and our confocality drop away very quickly. Here's what some of these Raman spectra look like. So these are all organic materials. So you can see there are similarities and there are some differences. But using the Polymer library we have with our products, it's really simple to be able to identify even similar different types of polymer materials. So in this next example, it's also a multi-layered laminate, but this time we've got a foil barrier. So this is typical when looking at packaging, where you want the foil to act as an optical barrier to stop normally sunlight from reaching through the material. It's using oil immersion in the same way with the same small 0.5 micron step size. Here we've got our oil at the surface. We've got a thick polyethylene layer, 117 microns thick. And then towards the end of that, before we get to the foil, we've actually got nylon present. Now, either side of the nylon, we're even picking up polydialyl isophthalate. So this is a thermal setting resin. So here, this is how we're adhering the different polymer layers together, the foil to the nylon to the polyethylene. And this is really relevant because we might want to understand any failures or any variations in this. So doing this for a single point, that's fine. That gives us this really useful information. But of course, we can do more than that. We can look at how it varies, not just in depth down through the x-axis here, but also how we can look laterally to that and look at effectively multiple depths at the same time. So this is an area. So if I put this so it's foil layer up, and then this is the actual data we collected. And you can see this is actually a volume. So we've got multiple depths in X and Y. And of course, we can turn these layers off. I can see the gap there where the nylon's adhering to the polyethylene. And then we can put those layers back together. So it gives us really good context of not just the layers, but how much variation there is in thickness across the sample surface itself. And so this is really useful for us to understand this. There's a couple of examples there looking at polymer laminates. Here we're looking much more now at the surface of these materials and looking often at very thin coatings. So the first example I've got is again with oil immersion on a multi-layered sample. And the aim of this work was to look at an acrylate layer, which was on the surface. Again, for my depth profiles, here you can see, again, this is very deep, going down 200 microns. We've got really good signal and good information here about these layers, but we're also able to get this acrylate layer right at the surface there. So we've got 4 layers, and the acrylate layer is about 3 microns thick. Even though this type of work is optimized to look deep into the material, you can still get some really nice information about what's at the surface. But when you're looking right at the surface, you don't necessarily have to use oil immersion. So here and now I've got a dry objective. So this is going back to just the air objective. And we want to look at this, a silicone layer at the very surface of a polymer material. So this is PET. So I've got a really small step size. This is 0.2 microns now. And you can see I've got a depth slice. So this is my silicone layer. It's about 1 micron thick. Above this, I've just got air, and below that, we're going into the polyethylene terethlates. And you can see here with the depth slice, again, you've got really good context and information about the uniformity of that silicone layer, how thick it is and how that varies, so that you can see how uniform this appears. The spectrum of the silicone is really quite weak compared to the PET itself. So the PET is in black. Here you can see the bump here from the silicone band. So this is actually from the silicon oxygen stretch and the vibration within the silicone itself. But silicone's so often an important coating to allow laminates to be separated and peeled away. So now I'm going to turn my attention away from looking into materials and performing confocal depth profiling. Now we're going to be looking at sections and polishing and mounting those sections to perform Raman imaging on the surface. Often these are prepared by mounting and polishing cross sections, but they don't have to be mounted and polished. I actually have an example where we don't have one like this as well. There are several benefits to working like this. So we don't have to worry about the refractive index. We're not looking into a material. However, it does make it destructive. We do have to prepare our sample in some way. The analysis itself isn't destructive, but we've had to do something to our sample, and it's obviously not going to be easy now to perform other analytical techniques. But we can achieve higher spatial resolution by working like this as well. So definitely there are some scenarios where working like this is beneficial. When we do this type of work, often the samples aren't flat or level. So even if they're polished and mounted, the way it's been polished and the way it's presented to the system often means that it's not perfectly flat, especially given that we're using high magnification objectives here with a very small depth of field of only a few micrometers. That means that we often have to focus the sample during data collection. And we do this using live track in the InVia Qontor Raman system. So live track automatically focuses the sample as it's moved to make sure that we're in focus onto the surface of that material. Not only does that give us really high spatial resolution for our chemical images, it also gives us some topographical information about the sample surface itself. Here I've got an example where we've got toughened polypropylene. So this is using a combination of polypropylene and isotactic polypropylene. This isn't prepared, and you can see we've got a really large variation in height. So this isn't a Raman image, this is purely a topography image from live track. The variation in height is around about 80 microns, and not only do you get the total height change, but you get all the subtleties of the morphology of that surface as well. And of course that can be really useful and complementary to our chemical information. Here's an example where we've got a sectioned material. This has actually been polished, and this is looking at a reinforced polyethylene resin. So here I'm actually using streamline imaging, and I'm using a different laser wavelength because of the information I'm looking to get from some of the glass materials. Here I've used live track. So live track's showing a variation. It's actually showing quite a big variation of about 2 millimeters. You can see that actually this is mostly because of a slope. So at the top it's lighter and at the bottom it's darker. So this whole sample slopes slightly. But even on top of that, you can see some of the features that correlate to different parts of our sample itself. And of course, you kind of expect that even from something that's been polished, because some materials are going to be worn away more quickly, and so you're going to get these subtle variations in your height depending on what the material is at different positions. The chemical information shows us that there's actually lots of different types of glasses within this. So this is a glass reinforced polyethylene sample. And I think what's interesting here is, as well as the different numbers of glasses in there, including quartz, you can see that one of the forms of the glass is primarily on the edge of the section. So it gives you information about the distribution and the domain size as well. And if we want to, we can go off and we can quantify that to be able to compare and to be able to optimize. Because we've got live track and we've got this 3D surface, we can put our chemical image on top of that as well. So this gives you a really nice representation of what's actually there on the sample, both in terms of the chemical information, but also in terms of the morphology and the slope that might be present. So the next example is a similar type of study. Here we're looking to analyze for graphene oxide within the polymer material. And so often now graphene and graphene oxide are really important because of their properties and understanding the effect it has on the property, but also what we've got chemically, so the distribution and the particle size is relevant as well. Here we've frozen the sample in liquid nitrogen, and then it's been fractured, so we can look at the interface at the fracture points to determine the presence of graphene oxide. So here's the live track morphology image showing a variation of about 92 microns. We can show that as a 3D surface. So you can see quite nicely here the sort of stepped interfaces where we have those fractures that have occurred. And here's our chemical image of the polymer in blue, but also of the graphene oxide in red. And we can see the presence of this not just on the surface there, but also in the fracture region itself. So this can give us useful information about the fracturing process and the role that the graphene oxide might be playing in that process. Looking at this as a 3D image, I think, is a really useful visualization tool to understand what's present and where it's present. So now I'm going to pass over to my colleague, Sarah Scheidler, who's going to be talking to you about microplastics.
Hi, Tim. Thanks for the introduction. The ability of Raman spectroscopy to aid in the identification of microplastics particles is made possible through the same type of confocality of the Raman microscope that you discussed for the laminates. The presence of microplastics is ubiquitous at this point, with research finding them in our freshwater sources, in the tea that we drink, to the intestines of the fish that we eat. Current research is suggesting that the majority of the microplastics, especially those found in our drinking water, are less than 5 microns in size. High confocal Raman measurements, which can sample sub-micron particles, is uniquely situated for the non-destructive identification of these types of particles. In this portion of the presentation, we'll focus a little on the sample preparation required for the analysis of microplastics, and also some of the new software features which enable and speed up this analysis. Typically, microplastic samples, no matter the source, be it from clean drinking water or even from the intestinal tract of a fish, are prepared by depositing the particles onto a filter for analysis. Really, the key to being able to successfully identify these particles is to obtain a sample which only contains particles of interest. For simple cases, such as drinking water, which can often contain low levels of particulate matter, this typically just involves filtration. However, the choice of filter will be critical for the Raman analysis, and we'll discuss that next. For more complex cases, where significant competing material is also present, such as material removed from an animal, much more processing is required to ensure that this does not impact the ability of the Raman to identify the particles. Multiple sample preparation steps involving dissolving material and filtering several times is often necessary. For these samples, the choice of filter can significantly impact the quality of the Raman analysis. The goal is to obtain an optical image using bright field, dark field, or other microscopy techniques, where there is a contrast between the particles of interest and the filter so that the particles can be easily identified. Filters with rough surfaces, or even filters that have been processed with certain chemicals during the filtration, might have additional features which would be hard to distinguish from the particles of interest. Another thing to consider would be that a number of filter materials themselves produce a Raman spectrum, which might interfere with the materials we are trying to identify. We've had success with measuring silicon filters or other metal, such as gold-coated filter options. These filters either have no Raman contribution or have a known Raman spectrum, such as silicon, that we can filter out. It's going to be important to get the right filter for the specific application. I mentioned previously that the goal is to obtain an image where we can clearly see our particles of interest and distinguish them from any background. We've used some different microscopy techniques, bright field, dark field, polarized microscopy, to generate this contrast. And we've found that for these particles on a silicon filter, that dark field often provides the best level of contrast. Once we have our image, we can bring it into our particle analysis software to identify the particle locations, allowing us to only do our data collection at the particle locations. Typically, for the microplastics, we have success using 785 nanometer excitation, but we can also collect data with any of our other wavelengths, 532, etc., for particles where maybe we have some strong fluorescence. The other thing to note here is that the image can be taken with a lower magnification objective, which will allow us to collect a larger area of our sample in our image. But then we can switch to a higher magnification and higher numerical aperture objective for our Raman data collection, so that we are collecting a highly confocal measurement where we're only collecting Raman data from the small particles of interest and not from our filter or substrate. For this example, we've used our particle analysis software to aid in the data collection and also identification of these particles. Here we can see a list of all of the particles that we've identified on our filter, along with the Raman spectrum that was obtained at each particle location and a small thumbnail image of each particle. We use the chain functionality within Wire to process this data file, doing a baseline subtraction from each spectrum, as well as a library search. Here we've filtered our library search based on the different materials that were identified. We can also pick out ones that were of lower quality, and we can either rerun them or reanalyze them, either increasing the exposure time or switching to a different laser to potentially avoid fluorescence. After we are satisfied with the material identification, we can then look at our tabulated results. From this filter, we have almost 700 particles that we've identified, some as plastic materials such as polypropylene and polyethylene, other inorganic materials such as calcium carbonate and titanium dioxide. And we also see some dyes. This can be very common with colored plastics. We can then look at the distribution for each material as far as the particle information, such as the equivalent circle diameter. We can generate a false color image where we color each particle according to its material identification so that we can quickly visually identify the distribution of different materials along our filter. Our last example that we'll walk through in this webinar touches on some of the work that's being done to investigate what happens to plastics after we throw them away. And in this case, we'll be looking at biodegradable plastics. So biodegradable plastics are made from sugarcane or corn, and they decompose with the surrounding moisture and temperature from the environment. So for this example, we have a biodegradable plastic container and the inside of it. And we can see that there's some color change between the outside and the inside of this container. Now, in this case, the blend was made from a polylactic acid, natural rubber, and a blending agent. Some of the chemical changes that occur during the breakdown is the hydrolysis of the polylactic acid with the cleaving of the carbon-oxygen ester bond by water molecules. The product of this reaction may contain fragments of lactic acid, oligomers, and other water-soluble products. These shorter chains can then be consumed by microorganisms. So for this example, the material was investigated with Raman spectroscopy to look at the stability of the biodegradable plastic after 4.5 years. This image shows a cross-section of that biodegradable plastic box that we saw on the previous slide, where we can see that one side, the top, was exposed to the environment. And we can clearly observe a color change in this material from the top to the bottom surface. And we're actually going to use Raman imaging to probe what has changed within the material. In this case, 3 Raman maps were generated, one from an area at the top, the middle, and the bottom of this cross-section of the material. Using the Raman image, we can look at the distribution of materials in each area that we sampled. We see the polylactic acid in white, the natural rubber in red, the epoxidized natural rubber in green, and the polyethylene in blue. In this top section, which was exposed to the environment, we don't see the presence of any natural rubber. And as we start to move into the plastic, we see the epoxidized rubber and polyethylene. The middle section contains the naturalized rubber, and as we move through into the bottom section, we again see the natural rubber and polyethylene throughout. But as we reach that bottom edge, the epoxidized rubber is no longer present. These types of Raman images can give us insight then into the chemical reactions occurring in the biodegradable plastic during the breakdown process. Throughout this webinar, we have discussed a number of areas within the field of polymers and plastics that can be probed with Raman spectroscopy, including we can use depth profiling and volume mapping to look at thin layers within a laminate. We can take advantage of the high confocality of a Raman microscope system to investigate materials along fracture sites and cross-sections of biodegradable materials. And we can also collect high signal-to-noise data to aid in the identification of microplastics in drinking water. All of these techniques are possible with the flexible InVia Raman microscope, making it a suitable Raman system for investigating a wide variety of plastic materials. I would like to thank you for your attention, and I'll turn it back over to Carrie now so that we can begin to answer some of your questions.
Thanks so much, Sarah and Tim. Great information as always. And I will invite you on camera. And Sarah, I know you said that you had some questions that you wanted to ask Tim, so I'll pass it over to you. But before I do that, I'll make a note to the attendees. If you have some questions, please feel free to ask them now using the chat. And if we don't get to them today in the Q&A, we will have someone follow up with you via email. All right, so hi, Sarah. Hi, Tim.
Hey.
Hey. All right, so I think we'll start it off. We had a number of questions kind of about depth profiling. So I was wondering if you could talk a little bit about the spatial resolution of layer thickness, and if you have some estimate of that.
Yeah, I should have probably put a bit more in the presentation about that. We had a few questions about how small a layer you can see, about spatial resolution, particularly in the z-axis. So, I mean, conventionally, we think of about 1 micron as being a fairly standard thickness to be able to see without too many issues. We can definitely see thinner layers than that as well. If we think about polymer materials in particular, then going down to sort of half a micron or so, even maybe a few hundred nanometers, that's definitely possible. As we look at other materials, so particularly materials that might be stronger, then we can then think about going down to really thin levels. So even monolayer type materials, we think about graphene, and certainly carbon is a conventional material for us to get that kind of thickness as well. So it depends a little bit on the material itself, but I would say sort of half a micron to a micron is pretty conventional. Yeah, so I think that's the kind of level that generally we think about.
Perfect. And then I guess going along with that, when we were talking about depth profiling, we've had a couple of questions about how long it takes to collect these depth profiles.
Yeah, so I mean, the standard depth profile is a pretty quick experiment. So, obviously it depends on how many spectra you collect, how far you want to go, but generally you're talking about minutes, certainly not hours. So I would say anywhere from a few minutes up to maybe 20 or 30 minutes for most of this type of work.
Perfect. Can you also talk a little bit more about sample preparation? And specifically, we've had some questions about if the sample needs to be transparent when doing depth profiling, and if anyone's looked at carbon fiber composites, and we've investigated them this way.
Yeah, sure. So if you want to do depth profiling, if you want to look into the material, then the material has to be transparent to the laser information. So it doesn't necessarily have to be transparent by eye, depending on the laser you're using, although that is typical. I think the question about the carbon's a really interesting one, actually. So many polymer materials have got carbon within them one way or another. And so that's quite a lot of the work that we perform. So the main issue with the carbon, apart from limiting the transparency, is really to do with the spectrum you get from the carbon itself and how that might interfere with the polymer spectrum. Because of the black material, you can get quite a strong absorption of all the laser light. So you need to be particularly careful with absorption of that laser and any kind of modification of the material. Often we would tend to go to a laser wavelength actually slightly below 532 nanometers. So often we'll go to a blue laser, and that can definitely help with those types of materials. And yeah, so some of that work's definitely performed, but certainly it's very problematic to do any kind of depth profiling on carbon-based materials. They're just not really transparent enough for us.
Perfect. And I think you also answered my next question, which was about potential sample fluorescence and how you might avoid it. So you were talking about changing to a different laser excitation wavelength,
Right.
and usually moving either more towards the blue or towards the red might help avoid
Yeah.
that.
Yeah, and I think for the carbon in particular, you go to the green because go to the blue, because as you go into the further into the infrared, then obviously you're starting to add more heat into the material, and that can make it worse actually for sample damage. In terms of fluorescence, I mean, we've got loads of options in terms of whether you go to a lower or higher wavelength. So we can go into the red or the near infrared. very much depends on the material. Of course, with some polymer laminates, you've got different materials and they might react differently in terms of which might be fluorescent using particular lasers. But I think most of the time, a green laser gives us really good information for these types of polymer materials and the laminates. And then other than that, we probably shift to a 633 nanometer setup. One of the downsides of going further than that is that you can start to affect a little bit your confocal performance and that spatial resolution that we can achieve.
Perfect. We've also had a couple of questions about if you can do confocal analysis within either like a hot cell or a within a cryo cell, so being at really cold temperatures specifically for graphene. So
yeah, so the objective is one of the kind of primary drivers of the confocal performance, so the numerical aperture of the objective. If you're within a cell, you probably can't get as physically close to the sample with the objective. That means we generally need to use a longer working distance, and that can definitely sort of reduce the NA, which in turn reduces the confocality. However, there's some really good long working distance times 100 objectives with some quite high NAs. And if you want to do really confocal work within these types of cells, that's probably the best setup to use. Other than that, there's some fairly conventional long working distance times 50 objectives as well. So it very much depends on how confocal you want to be and what the practical limitations are with the cell you're working with.
Great. All right, so let's switch a little bit and talk about the particle analysis, especially for microplastics. So we've had a couple of questions about if you can achieve submicron analysis of different particles that you might find.
Yeah, absolutely. So again, the laser spot size is somewhat a factor of the objective and the laser wavelength. So most of this work, we'd use a 532 green laser. If we use a times 100 objective, then our spot size is submicron, so it's around sort of about 600 nanometers. And at that point, we can see any particles of that size or larger, and even particles smaller than that. We can actually see those as well. So for example, you could have a particle 100 nanometers in size. You're analyzing that with a 500-600 nanometer laser spot. You still can get a spectrum from that particle. You'll still possibly be able to size that optically, but then of course we're kind of on the limit there of what you can achieve from the diffraction limit. So getting a spectrum from that material, absolutely. The limit in terms of the size you can see, probably down around a few hundred nanometers with that kind of magnification setup.
Perfect. And then we had a follow-up question with that, which was how many particles we could analyze at one time with the particle analysis software. And I mean, in my experience so far, the answer has been thousands. So you can just have an image, have it identify thousands of particles and set it up, let it run and do its thing.
Yeah, absolutely. And I think when you think about what you're trying to achieve by using it in that kind of way, because the alternative would be to do Raman imaging where you're getting many spectra and you're getting that in a slightly different way. With the particle analysis, you're going to the center of each particle and getting a spectrum just from that position. So I would say overall, there's probably slightly less of a need to look at thousands and thousands, but we can look at tens of thousands of particles with particle analysis with no problems.
Great. Can you talk about how you might use Raman in relation to like other analytical techniques which might be found in Polymer labs, and if you can use Raman in combination with those techniques?
Yep. So we've talked about Raman, particularly when looking at laminates being sort of non-destructive and almost no sample preparation at all. So that makes the ability to use other techniques just really easy and really kind of pushes you towards doing Raman analysis first, rather than going to a technique where it might be destructive and it might mean you've got to adapt your sample in terms of preparing it for that particular technique. So I think it's a really complementary technique, not just in terms of the information you get from it, but in terms of the sample preparation steps and how that fits in with other techniques as well. If you did want to use other techniques first, perhaps, then we also have some software that allows us to correlate information from one technique with the Raman analysis. That means we can go to those same positions to get Raman data from exactly the same locations. And that means you've got this really nice complementary information from multiple techniques at the same locations. Or if you want to, you can actually import chemical images from other techniques. That can be optical, or it can be really from any technique whatsoever. And then we can perform Raman imaging over those same areas as well. So quite a few different options that make it a really good tool to fit with other methods.
Great. I think that's answered all of our questions.
Awesome. Thank you so much, guys. And thank you everyone for joining us. And I just put on the screen some information on our next webinar. We will have 2 of them to hit a few different time zones for some of our European friends. So keep an eye on your email for that. And as mentioned, we'll send a follow-up email with the recording. And if you did ask any questions, we'll answer them via email. Thank you all and have a great day. Bye, guys.
Bye.
Bye.